Let's have a look at the simplest linkage between IC design and layout. 我们来看一下哈，那个 layout 跟设计那个最简单的链接。Anyway, MOSFET is some kind of three-dimensional device. That is 3D. Okay. Anyway, this is some kind of bird view or three-dimensional view. We have gate. This is gate, and then gate oxide in between, source and drain, and in the middle, the channel or the body. However, for layout, we wouldn't like to have such kind of three-dimensional view because it's too complicated. For most of the engineers, I don't think they can handle such kind of 3D structure. Yes, we have some EDA tool to deal with such kind of three-dimensional layout, but usually it is too complicated. But why we have such kind of 3D layout tool? To get much better understanding about the final result, especially the parasitics. If you are talking about parasitic capacitance, blah, 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 I think three-dimensional view will provide much help. But usually that's too complicated. So most of the layout engineers, they are happy with such kind of 2D layout view. All right? So that is the true three-dimensional device. But for layout, usually we are happy with this. Okay? So it looks like a flat. The gate looked like a flat line. No. In the past, it looked like that. That is, again, for such kind of 0.35 micron or even older processes. Nowadays, it is more flat than this, much flatter than this. But it will go down a little bit at the edge, then come back. Got it? Okay, if I have a cross-sectional, a cut line here for you to view, in the past, it looked like that. And nowadays, with STI, at the boundary, it goes down a little bit, then go back. Nothing is perfect. Never expect it is flat, totally flat, just like this. No. Forget about it. Okay, so this is the poly gate. We have poly contact. And then you have source and drain area, right? You have source contact, you have drain contact. And then where is the body contact? As I told you, as close to the MOSFET as possible. For 0.18, yeah, it can be allowed around 25 micron far away. It doesn't make any sense for analog IC designer. Okay, because if your body contact is here, you ground it. Don't tell me the channel will get exactly the same 0 volt for bias. No. Okay? Oh, first of all, for all those connections, we call it contact, because it only metal one can contact all the layers below it. Okay, so we call it contact. Never mind to contact poly or to contact source, drain, or body. We don't care. All those connections are called contact. However, above metal 1, between metal 1 and metal 2, metal 2 and metal 3, all of them, all those connections are called vias instead of contact. Only below metal 1 are called contacts. Above it, all vias. All right? Oh, for regular MOSFET, source and drain are symmetrical. It means you can name it source, drain, or you can name it drain source, up to your convenience. Okay? For what? to simplify the routing. If source and drain can simplify your routing, then do it. If not, then change it. Drain, source, as you like. But it can only be applied for regular MOSFET. For high voltage MOSFET, source and drain are totally different. Okay? They cannot be reversed. Usually for high voltage MOSFET, the drain area is much larger than source, according to its natural structure. Okay? And then allow me to show you some of the parasitic capacitance. It has a lot of capacitance. Especially, I need to warn you. See? For example, this source, drain, and then P substrate. Again, we always focus on MOS for explanation. How about PMOS? Just think about it. The operation principle is quite similar to MOS. Okay, for source or drain, you can see we have the so-called PN junction here, here, and a little bit there. Okay, and according to such kind of PN junction, we have what? Capacitor, depression region, capacitance, as I mentioned in previous chapter. Okay? So, if we would like to reduce, or who dominates the parasitic capacitance for source and drain, we call it side wall, 边墙,侧墙, side walls. How many side walls you have? And in theory, 4. 1, 2, 3, 4. Got it? But for this side wall, actually, you can see the PN junction is really small because here we don't have PN junction. You have M+, I have a lot of free electron here. We converted from P to N type. M+ and M+. Okay? So, please pay attention. This portion and that portion. From M+, N to M+, sorry, no PN junction. No PN junction. Okay? At most, a small portion here, a small portion there. So, keep this in mind. The side wall, besides channel, connected to channel, has very few parasitic capacitance. Got it? If the channel is here, then this side wall has much less parasitic capacitance. For the other 3, 1, 2, and 3, they have 100% of the parasitics. The other one is bottom plate. Okay? You have N and P, and inside P outside. So, 3 side walls and 1 bottom plate dominate the parasitic capacitance for source and drain region. Got it? But for such kind of parallel pipette, it has 6 faces, right? So how about the top one? Does it has any kind of PN junction? No. You have N inside. Yes. And how about above it? Silicon dioxide. No P. No P-type semiconductor. Got it? So we have only 5 faces with parasitic capacitance. 3 side wall and 1 bottom plate dominate. And the inner one, I mean connected with channel, it has very few parasitics. Got it? So, if you would like to speed up the operation of the MOSFET, you had better reduce the parasitics for all those 3 side walls and the bottom plate. But how? By stack layout. 把它叠在一起. Later, I will show you. Yeah. Again, I told you already, MOSFET is some kind of parasitic capacitive device. Without capacitance, it doesn't work. We are talking about the capacitance above the channel, the silicon dioxide, and then the gate. That is the main focus for capacitive MOS operation. Okay? And humankind tried to increase C-arcs, as I mentioned already, because it can help us to reduce VTH, blah, 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 to speed up the operation. Oh, it's really good. Anyway, for each process, gate oxide is the thinnest. Okay? Never mind for what kind of layer. Gate oxide is the thinnest. Gate oxide 是最薄的. Why? Again, we would like to increase it to speed up the operation. So it means if you would like to get the most capacitance, you had better to focus on gate oxide. But how? Okay, gate as one terminal. And the other terminal should be channel, right? But channel has no connection. Luckily enough, channel is connected with source and drain. So the second terminal for your capacitor can be source and drain connected together. So you have the first terminal with gate and the other terminal with source and drain. And it will behave like a capacitor. The best capacitor, I mean in capacitance. For the same area, it can generate the most capacitance. Why? Because again, gate oxide is the thinnest for all the layers. Okay? 同一制程里面所有的层那个 gate oxide 是最薄的，所以它的那个容值是最高的。Oh, that is good. But it is also bad because this is the most capacitance. It looks like that. Even though it can generate the most capacitance, however, the capacitance is not constant. Okay? The capacitance is influenced by the terminal voltage, VGSD. Okay? Substantially, it looks like that. It's really upset. For real, for perfect capacitor, it should be flat. Never mind what the terminal voltage you have. Yeah, right? Never mind what the voltage is. The capacitance should be constant. That is for ideal case. However, for most capacitor, it looks like that. It's really upset. That is really, really bad. But again, it is also good. Why? That is the easiest way to change the capacitance on chip. In the past, we have radio, analog radio. It looks like this. We have a window, a pointer, and then you have a lot of FM, AM frequency, right? And that is a rotor. You can rotate it, and then the pointer can be shifted upward or downward. Yeah, to change the tuning frequency. In brief, for such kind of analog radio, the frequency, yeah. Okay, it is proportional, reversely proportional to the square root of LC. Yeah, how to tune the frequency? ICRT, 100.7, right? And some kind of a classic radio 98.1, blah, 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 blah. How to change the frequency? You can change either inductance or capacitance. But to change inductance, I think is much, much harder. So usually we change the capacitance. But how? We have something called varactor, 变容器, variable capacitor. That is the name, that is the meaning for varactor. Okay? So what is the idea for varactor? It has stator. Stator means it is static. It doesn't move. And the other one, rotor, it can be rotated. So you can see two of them. If they are 100 overlapped, you have the largest capacitance. Okay, but you can rotate it. What? The stator here, the rotor there, right? So the capacitance can be approaching zero. So we can see we can tune the capacitance from 1 to 0. Yeah, with such kind of varactor, very good. We can change it. But how can we implement anything like this on chip? It doesn't make any sense. IC means solid state circuit. Everything is solid. So I don't think you can rotate anything on chip unless you apply MEMS. MEMS is possible. MEMS is possible, but you need extra cost. All right? So the simplest and the cheapest to tune the capacitance is this. Bingo. Yeah, you don't need to rotate it. No. You only need to change the terminal voltage. That's it. The voltage here, the voltage there, blah, blah, blah. All capacitance will be changed substantially. Okay, and this is very important. For such kind of MOS capacitor, it's very important for RFIC. Now for radio frequency chip design. Again, I don't think anybody would like to change the inductance on chip. Yeah, that is too hard. So we change capacitance. And this is also the most popular on-chip varactor. Okay? So again, it is bad, it is good, it is bad, blah, blah, blah. For analog IC designers, you need to pay attention not only the good issues, but also the bad issues. For example, this is bad because the capacitance changes a lot according to terminal voltage. But this is also good. It can help you to change the capacitance when necessary. Okay? That's it. And again, the capacitance for source and drain area, I explained already. We have 3 side walls and bottom plate. Those 4 faces dominate the parasitic capacitance. If you would like to speed up the operation, you had better reduce it. But how? Just like this. See? That is the regular layout. So you have 3 side walls, 1 bottom plate, 3 side wall, 1 bottom plate, right? How to reduce the impact? See? Allow me to show you another one. And overlapped with each other. Please have a look at the middle region. You can see your drain and my drain overlapped together. Okay? So we have only 2 side wall. The short side wall instead of the long wall. No, the short side wall shared with you and me. Oh. And how about the bottom plate? Only 1 bottom plate. Also shared with you and me. Bingo. So in the middle region, on average, each MOSFET only need to share 1 short wall and 50% of the bottom plate. for parasitic capacitance. Got it? And how about the boundary? Oh, sorry. The same. 3 sidewall, 2 short, 1 long, and the full, 100% of the bottom plate needs to be on your side. Okay? You need to carry the heavy duty for 3 sidewall and 1 bottom plate, but in the middle, only 1 short sidewall and 50% of the bottom plate. In this way, we can reduce the capacitance in the middle region. So it means what? If you have a long, I need to say wide transistor, don't do any layout like this. You are the better split it. Okay, you say, hey, this is source, that is drain, and this is also source and drain. Then you flip it to become drain and source. Then overlap the drains. Look like this. So totally, the overall parasitic will be reduced. Okay? Then you say, hey, I can do the same thing again and again. You say, hey, look. I also, oh, sorry. I cannot plot over here. I also split it. Come on. Does it make any sense? No. Okay. We have some limit to apply such kind of stacked layout. 堆叠式的 stacked. Okay? If you have a long one, such long, then I cut it, it becomes this and that. Then, okay, I can still cut it, blah, blah, blah. Finally, if the layout after overlapped or overstacked is about a square, don't cut it further. Okay, just like this, it looks like the overall layout look like very close to squared. Don't cut it. Why? Because if you cut it, then the area will be splitted. You need to generate 2 side walls. Okay? So what you can gain, if you cut it here, then you have, two side walls, 2 short side walls, two, right? And you overlap this long side wall to that long side wall. That is what you can save. You save only this, but you sacrifice 2, 4, 6. 你聽有吼？你也差不多正方形都冇個切的呀。你個切的哈，你切的所在會產生2個 side wall， 2個側牆，短的側牆會跑出來。結果你就袂好啊，哈。Yeah, just apply such kind of concept smartly, intelligently. Don't apply it again and again. No. So the final target is to make the overall layout as square as possible. That's it. Okay, no more. Yeah, and we are talking about the junction capacitance I mentioned already in previous chapter. Okay. And then I need to warn you, for such kind of CMOS structure, we have MOS here and PMOS inside and well. And I help you to draw some of the parasitics. I can see. Okay, for such kind of parasitics, if you rotate it with 90 degrees, it looks like that. For such kind of circuit, it is called SCR. Okay, it is used in power electronics, blah, blah, blah. All right, and the parasitics look like that. Usually, we operate here, okay, in this region. For example, you turn it off, 0. You turn it on, VCC, 1.8 volt or something. Okay, so you turn off, you turn on. Turn off means 0 current. Turn on, the current, the leakage current, I mean from here to there, from here to there. Okay, the leakage current here is really, really small. It is not 0, but very, very small. So it doesn't waste too much of your power consumption. 它不会浪费你太多能量啊，因为这边的电流非常非常小。The problem is nothing is perfect, even for your VDD. If you measure your VDD on chip, okay, it doesn't look like that. No. Especially for digital circuit, you have a lot of spikes. Because you have reference clock to turn on, turn off many of the circuits, right? How many transistors to be turned on, turned off? For A14, I told you already, more than 10 billion, 超过100亿颗 transistor to be turned on and turned off. According to your rising edge or falling edge of the reference clock. So it will cause a lot of spikes. All right? So what is the consequence? Here is your VDD. But if the spikes goes too much over the tip point, 转折点, then if you're unlucky, it will go down there. If you are lucky, it will go back. But usually, it won't. Okay? So, your VDD here and too much spikes, it is more likely to go, you go up and then back to normal, right? So it means you are here, but that is VDD. The spikes goes up and down, unlikely enough. It will more likely be there. Then the leakage current is much, much higher than before, right? And I would like to turn it off. Oh, sorry for that. Here, if we would like to turn it off, it will be shifted to there. It doesn't have any chance to go back, right? So even you would like to turn it off, you can see a lot of current here, leakage current. And the chip is more likely to be burned. Okay? So this is the so-called parasitic SCR structure. It's really harmful according to the ripples or spikes on your VDD. And it happens always. Okay? The VDD is not a flat curve. It is not fixed. It's too dangerous. What you can do? Okay. You had better don't turn it on. But how to turn it off? The voltage here, the voltage there, had better be as small as possible. Got it? How to make the voltage here or there as small as possible? You need to reduce the parasitic resistance. How? Body contact. Okay? The more body contact in P substrate or inside and well can help you reduce. The more contact, the less resistance. Congratulations. Yeah. You can kill the SCR structure. If the R here or there really small, they will be shorted. Okay? No conduction at all. That is good for you. And again, this is what analog IC designer needs to pay attention to. For such kind of very little detail, very small detail. Never mind how small the detail is, you need to pay attention to. Otherwise, you will get a lot of trouble, even with such kind of SCR, parasitic SCR structure. More likely, after turn off, your chip will go there to conduct a lot of current, to waste a lot of power for that. It doesn't make any sense. Okay, let's go further. Yeah, as I mentioned, usually for your hand calculation, we can focus on such kind of small signal model. Okay, and again, what is the definition for small signal? The operation region for both your input and output should be very, very small. Then you can pretend everything is linear. We can apply such kind of We call it linearized model for easy calculation. 线性化的 Okay? For large signal one, sorry for that. Our brain is too small. We cannot handle such kind of nonlinear model for hand calculation. No. Okay, and allow me to show you, I think you learned it already from microelectronics, but I would like to show you this. For microelectronics, you have only this, right? However, for analog IC design, you had better consider your body effect. Unless you promise me you don't have any body effect. For PMOS, it's totally possible. Because PMOS is inside and well, right? So it is inside and well, so you can connect your body contact of the and well to what? To your source. Bingo. That's it. Okay? But, for example, if you have such kind of, nothing is free. Okay? You have P1, you have P2. Yeah. Usually, if you put P1 and P2, this is VDD. And that is to MOS. Okay? Oh. Usually, if you put P1 and P2 inside the same MOS, oh, sorry for that. Because your body and his body should be exactly the same angle, then connected to VDD. Then P2 needs to face some of the body effect. All right? So how to eliminate all the body effect for such kind of stacking structure? You need to have separate angle. Okay? Then you can connect your body to your source. And then his body to his source. Congratulations, no body effect. All right? But it is a little bit more expensive because separated angles means what? Larger layout area. You need to have some kind of spacing between different angles, especially with different potential. The potential, the body voltage here and there won't be the same. Okay? Yeah, and how about MOS? Can you eliminate the body effect for MOS? Yes. You need the help of what? Deep and well. Okay? Later, maybe, if I have time, I will show you that. Okay, I have time. All right. How about well? How about MOS? Right? N1, N2. The same if without any well, N1 and N2 are fabricated in the same P substrate, right? Then their body needs to be connected. Sorry for that. This one has some kind of body effect. Okay? Then what you can do? Deep and well. And you cannot apply angle. No. If you apply angle, inside the angle, you can only fabricate PMOS. Okay? You cannot fabricate NMOS inside angle. Then it will become depression type. It doesn't make any sense. Okay? So we need the help of deep angle. So what is deep angle? Okay. Since it is deep, so it is deeper than such kind of angle. So this is the deep angle. Okay? And then inside deep angle, you can fabricate P well. Got it? And then MOS. Got it? So the structure look like this. Deep angle. Then P well. P well behave like P substrate. So you can have your MOS inside. Okay, that's it. That is almost only one way for you to eliminate the body effect for MOS. I mean with P subject. Okay? But nothing is free. You need to pay the extra mask cost for deep and well. It takes some money. All right? Yeah. If you cannot eliminate the deep and well, the body effect, then you had better consider such kind of body effect. And I told you already, body can be viewed as the second gate. It can also used to control the current. So you have the main GM. It is controlled by gate. Okay, and then the other one, G and B. B means body. You can see the direction are exactly the same. The higher gate or body, the more ID, the more current at the source, at the drain or source, as you like. Okay, that's it. Yeah. If you consider even more, not only the main small signal, but also the parasitic, capacitance, or even resistance, it will be too complicated. It is no good for our human brains. We are happy with this and forget about all the parasitics. But why I still show you this? I will only like to warn you. Nothing is perfect. We have a lot of parasitics. How to reduce the parasitics? Usually by good layout instead of good circuit design. Okay, usually not. Yet again, this is what I show you. Yeah, you split it, source, drain, and then change drain to source. Then they can be overlapped. Our drain, source, source, as you like, I don't care. Not only the parasitic capacitance will be reduced, but also, you can see, for the gate, polysilicon is no good for conduction. Okay? The conductivity of polysilicon is much worse than monosilicon. 多晶系的导电能力比单晶系还要差。It means the parasitic resistance of gate actually is quite high. Alright? So if you split it, then stacked altogether, you can see, RG is reduced by 2. And then connected 2 in parallel. So by 2 again. Congratulations. The overall gate resistance will be reduced by 4. Got it? That is what we can do. Because the delay usually proportional to RC constant. Right? So with stacked layout, we can reduce not only C, but also R. Congratulations. The operation speed can be much, much higher than the original one. Okay? Yeah. If you would like to, again, go to the bottom. 打破砂锅问到底. Allow me to show you some of the details. Even more parasitics. As I mentioned, and then you have a lot of terminologies. 有一大堆的名词. Then, in the SPICE model, if you are interested, you can open the file, open the technology files according to models. You can see for only a MOSFET, never mind MOS or PMOS, I promise you, more than 100 parameters. Okay? And you can ask your teacher how many he or she knows. Very few. Okay? So, all those models, all those parameters are good for device engineers, not for analog IC designers. You only need to know some of them. Okay? For myself, I think I can read more than 10. That's it. But 10 out of 100 only means I know less than 1/10 of the parameters. Who cares? Yeah. Anyway, I show you this only to warn you. There are a lot of parasitics. You had better apply good enough layout to reduce them, to enhance your performance. That's it. I wouldn't like you to remember this. No good for your design. Only be very careful. Very terrible. That's it. Good enough. Okay? Don't go to the bottom. Just try your very best to apply good enough layout. I mean the layout making sense to reduce the parasitics, to enhance the performance good enough. We have a lot of layout skill to do such kind of performance enhancement. Okay, allow me to show you some of the layout example. Yeah. Here is NWell. Allow me to highlight it. Out of NWell, we have MOS inside P subject. For MOS, to enhance the conductivity, both the source and drain are doped with M+. But what is the type of body? Body is P subject. It should be P type. Okay, so we need to have P plus doping to contact the body for the MOS. On the contrary, PMOS is inside NWell. So both the source and drain are highly doped to be P plus, right? But again, how about the body contact? Again, the body is N, right? So you need M plus doping. Okay? So you can see, for MOS, only the source and drain are M plus doping. The body should be P plus doping. On the contrary, for PMOS, only source and drain are P plus doping. The body should be M plus doping. That's it. So they try to get help from each other. When you dope here and there for MOS, you also dope the body contact for PMOS. That's it. They are fabricated at the same time. Also, P plus doping here and there are processed simultaneously. Okay, if you know how to do such kind of MOS layout, PMOS layout, and the body contact, blah, 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 then you can go for example, the simplest logic gate inverter. That is the so-called NOT gate. Okay? So that is the symbol. Oh, no. That is the circuit. We have symbol. That is the circuit symbol for inverter or NOT gate. And that is the schematic. And then the layout. However, even you have the schematic, how many layouts you can have? In theory, infinite. Okay? So as you like, I don't care. Yeah. And let's go for, not if you know how to do the layout for MOS, PMOS, you can not only do the layout for inverter, but also for transmission gate, 传输闸. Transmission gate is composed of, again, one PMOS, one MOS, but connected in parallel. How about the inverter? They are connected in series. Okay? 这是串联呐，还是并联呐 ？Anyway, yeah, you can do similar layout here. And after you know how to do the layout for inverter, for transmission gate, we can lay out even more complicated logic gate. For example, this is D-type flip-flop. Oh, I need to highlight that. I need to point out that for many of the digital gates inside analog chip, usually the layout is done by our hands. Now we have EDA tools to help. But usually, the layout from EDA tools, it is larger. I mean in layout area. And also, the performance is no good. Okay, our human brain is smart. It's still smarter, to reduce the layout area and to reduce also the parasitics. As I mentioned, we have many kind of skills to reduce the parasitics. So, with your own hands, but longer time, you can achieve better. I cannot say much better, but better layout, even for digital circuit. And this is the reason why all the IC design houses, they don't depend on TSMC's development kit. For TSMC, it has all the layouts required for such kind of inverter, flip-flop, accumulator, everything. But they have layout team to redo the layout for all the gates by themselves. And they don't show you the real content of the layout because they filed a patent to protect their own layout. Okay? Anyway, allow me to show you this. This is some kind of D-type flip-flop. Yeah, some kind of fundamental logic gate you required maybe to compose your counter 计数器, right? Maybe also accumulator. Yeah, 那个叫累加器. A lot of that. Okay? So, this is the, how can I say, quite similar to circuit, but instead, not in such kind of detail. All right? So you can see, if you need any kind of flip-flop, I think that is almost the easiest. All right? So we have positive cycle and negative. For the reference clock, we have positive and negative cycle. For positive cycle, it turns on here. Okay, it means you can and off there. Okay? That is the master and that is the slave. The so-called master slave D flip-flop. 主从式的 D flip-flop. D 型正反器. So the operation for the master and the slave are complemented. 它们是互补的. If I turn on, you turn off. Okay? And if I turn off, you turn on. That's it. So for the positive half cycle, on, off, on. So the input is red here. D bar, because it is some kind of inverter. All right? And how about the half cycle? Reversely. Off, on, off. Okay? Yeah. Then D bar is transferred to the output, become D. That's it. Another flip-flop. And you can see it is on. So two inverters connected in a chain, right? It is called a latch. 栓锁器. That is the most fundamental structure for SRAM. Okay? That is the so-called 4T SRAM. 4个电晶体构成的那个静态记忆体 for 1 bit. That is the most fundamental one. All right? Anyway, it is the so-called static flip-flop. All right? Even though you on, off, then off all the way. We don't care. The D bar here, D over there. You can hold the content of the input. Okay? With the help of latch. Without the latch, we cannot hold it. So, allow me to show you almost the final two. Okay? If you would like to simplify the D-type flip-flop even further, then you can get rid of this. Okay? The circuit size will be reduced by 50%. So it means what? In theory, the parasitic can be also reduced by 50%. Then the operation speed can be doubled. Okay? 因为电晶体个数减半，杂散成分减半，所以你的操作速度直接可以理论上拉2倍。And what is the operation principle? Okay, without this, without that. So again, for the positive cycle, it is on, that is off. So D here, D bar there. And how about the next cycle? Oh, off, then on. You get D. But the problem is, you can see, for the negative half cycle, it is off. Okay? Then D bar is here, but without input. There is no input. So we have some kind of memory because you have parasitic capacitor here, right? So during the first half cycle, D actually is held here with the help of your parasitics. So sometimes parasitics helps. Okay? However, the parasitic capacitance here is so small. So after some time, if you don't apply your clock, you apply high, then low, sorry for that. The information stored here cannot last forever. 存在这个杂散电容上面的资讯不能撑太久 because everything is leaking. 它们会漏电. Okay? So we call it dynamic D flip-flop. You need to operate at high enough speed to keep the information temporarily hold here correct. Yeah. Anyhow, allow me to show you the operation speed. For static, that is 0. Okay? That is the frequency. For static one, from 0 to some limit. And how about dynamic one? It is almost doubled. And how about the minimum, the lowest frequency you can operate? It is not only 50%, much lower than that. Much lower than 50%. So, for operation, dynamic circuit is much better than static one. The only problem is you cannot hold just like your SRAM, right? You don't read, you don't write, nothing will go wrong. But for DRAM, if you don't read right, it needs to be refreshed. Without a refresh, the content will become wrong after some time. Okay? Yeah. So, finally, allow me to show you a very fantastic layout for 4-input NAND gate. 4-input NAND means 4 PMOS connected in parallel, 4 MOS connected in serial. Okay? Then allow me to show you this one. Wow, fantastic. You can see 4 PMOS connected in parallel, and then 1, 2, 3, 4. Okay? All the way. From here all the way to the ground. From here all the way to the ground. So 1, 2, 3, 4. 1, 2, 3, 4. Okay? That is the most compact layout for such kind of 4-input NAND gate I had ever seen. Yeah, we have different IQs. Somebody has very good IQ at space. Okay, spatial IQ. 空间的那个智商. Somebody is quite talented. So if you have very good spatial IQ, then you can do much better than the others. However, if I am not so good as you, I can have a look at your layout, then learn something, right? That's it. Yeah. You don't need to be very smart, but you can still learn something from the others. Okay. Finally, before the end of the layout, I would like to highlight something for you. You can see for operation, all those 4 are in parallel, so they are symmetrical. Got it? However, how about N1 to N4? Forget about it. They are not the same. From N1, it needs to face more body effect. Yeah, the worst all the way to the best. Okay, so the operation for N1 to N4 actually they are not the same. So it means what? The operation speed will be different from N1 to N4, even though for PMOS they are symmetrical, but for NMOS they are not. Okay, so if you do very detailed simulation, I warn you, the propagation delay from input IN1, 2, 3, 4, all the way to the output, they are not the same. Got it? It is very dangerous for your PLL, DLL, blah, 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 because usually students with such kind of structure, especially with the circuit symbol, they look the same. 1, 2, 3, 4 to output. So supposed to be from here to output, everybody enjoys the same delay. No, sorry for that. From IN 1, 2, 3, 4 to output, I promise you, if your simulation is detailed enough, then you can see the difference. They are not the same. For all of them are not the same. Okay? It will hurt your high frequency, for example, PL, DL, blah, blah, blah. You will, with such kind of structure, you will get a lot of phase error. Okay, for high frequency lock loop operation. So what you can do? Again, this is good for digital IC designer, not good for us. If you are a picky, by the way, outstanding analog IC designer, you hope from 1 to 4 to face the same delay to the output. To kill such kind of phase error, what you can do? What you can do? Okay, allow me to show you one example for two. Only two, okay? Otherwise, it will be too troublesome for me. Okay? That is the original one. Good for digital designers, not for us. So what you can do? You need to split IN1 and IN2 into halves. Then, okay, 50% here, 50% there. So this is for IN1. 50% here, 50% there. This is for IN2. Then I promise you, it will be symmetrical. Got it? You need to be so picky. Then you will become very outstanding in the future design. In this way. One here, 50, one half here, the other half there. So you have some kind of cross-coupled connection for your input. Then you can make everything perfect to enjoy the same delay. Okay? I don't think you will learn this from your analog IC design. No, because even for Razavi or for Aaron, they all think, some kind of digital circuit, so forget about it. Sorry. I told you already. For almost all those digital circuits, especially for high-end digital circuit, we do the design and layout by our own hands. Okay? In this way, you can achieve the best performance, the best of the best. All right. So my recommendation for you is to be as picky as possible, to achieve the best analog IC design. Thank you.